Hey guys, welcome to our first video lecture for Psych 467. This series of recordings, these first three, are going to mostly be review from Psych 301. So you should be able to kick back a little bit and relax. The material shouldn't be too conceptually challenging, but I do recommend that you read sections 1.1 and 1.2 before watching this lecture for a bit of background information. Okay, let's get started. So in this lecture, we're going to first talk about what a variable is. In your study for 467 and 468, you're going to have three variables, two in which you manipulate and one that you measure. We're also going to talk about the types of research questions that statistics can help us answer. And so those types of research questions are going to be frequency questions, association questions, and causal questions. And then we're going to talk about how we can use small groups of people to answer questions about large groups of people. So in other words, how can we use a sample to draw conclusions about a population? Okay, so let's get started with the first question, which is, what is a variable? So a variable is anything that varies. And by varies, I mean that it has more than one value. So gender is a variable because it has more than one value or more than one level. At the very least, it has two. It has male and female. Your height is a variable. Some people are 5'3", other people are much taller, 5'8", some people are shorter, 4'6", right? There's different values associated with height, and so it is a variable. Now, some variables can be measured. And what I mean by measured is that we simply record an observation. In fact, all variables can be measured. And so here are some examples. Weight is a measured variable. We ask somebody to stand on a scale and we record what the scale says. We record their weight. Blood pressure would be another example of a measured variable. And then here on the right, we have the attitudes toward women's scale. And so here, this scale measures feelings about women's rights and gender equality. And so we can measure where people stand on women's rights by giving them this scale and recording their score. So notice for all three of these examples, and gender, if we include that as a fourth, that I am not, as an experimenter, I'm not manipulating, I'm not interfering at all with these variables. I'm simply recording the natural state of these variables without interfering with that natural state. Now, some variables can also be manipulated. And this is when the experimenter does exert some control, when the experimenter does intervene, when they do interfere with the natural state of things. And so this is when the experimenter would assign participants to different levels of a particular variable or to different conditions of that variable. So here are some examples. One is caffeine consumption. So if the experimenter wanted to know the effects of caffeine on memory, then he or she could take 50 participants and give them caffeinated coffee, right? So 200 milligrams of caffeine, and take another 50 participants and give them decaffeinated coffee, which has close to 0 milligrams of caffeine, and see which group of participants performs better on the memory test. So in this example, the experimenter manipulated the variable of caffeine level. Some participants were given a lot of caffeine, other participants were given close to none. Other examples would be how violent a video game is that participants have to play. So in this example, I think we've got GTA as the violent video game option and Tetris as the non-violent video game option. So participants play one or the other, and then maybe the researcher measures how aggressive they are in real life or how not helpful they are in real life. The third example has to do with seasonal affective disorder, which is when in the winter months, when there's not particularly a lot of sunshine, people tend to get a little down, feel a little depressed. And so there's some research that indicates that using a sun lamp, like you see in this picture, helps alleviate some of those depressive symptoms. And so to see if these sun lamps really work, you can assign participants to either spend 4 hours a day in front of the sun lamp or 0 hours a day in front of the sun lamp, and then see which group of participants has higher or lower depression scores afterward. So in all three of these examples, the researcher is manipulating that variable. The researcher is controlling that variable by saying, you're going to be in this condition and you're going to be in that condition. Now, there are some variables that can't be manipulated, either for practical reasons or ethical reasons. So from a practical standpoint, certain variables like a person's sex, their gender, or their personality, or their IQ, just simply can't be manipulated. People are what they are. I can't take a participant and say, okay, you're going to be male today, or I can't take a participant and say, you're going to be smart today, or you're going to be extroverted today. People come with those variables, and they're very difficult to change. Other variables can't be manipulated for ethical reasons. So although it's theoretically possible to do this, it wouldn't be ethical to do so. If I wanted to look at the effects of smoking on lung cancer, I could theoretically get 50 participants and tell them that they have to smoke 4 packs of cigarettes a day. That seems like a lot. And take another 50 participants and tell them that they're not allowed to smoke any cigarettes at all that day, and then measure their levels of lung cancer 20 years down the road. That is theoretically possible to do, but it obviously would be immoral and unethical, and so we can't do that. Okay, so now that we know what a variable is, let's talk about the types of research questions we can ask about the variables we're interested in. So one type of research question is called a frequency question. And here we're asking about the particular rate or level of something. When I say rate, I mean the frequency. We're asking how often does something happen. So for example, how many Americans eat breakfast? How often do people eat breakfast, in essence? Level is referring to ranking. So an example would be, what is the number one breakfast food in America? What one breakfast food is eaten more frequently than any other breakfast food out there? Maybe cereal, maybe bacon, maybe toast, whatever. Okay, the second type of research question is an association question. And this type of question asks whether two variables are associated, hence the name, or whether two variables are correlated. Association and correlation mean exactly the same thing, so you can use those two words interchangeably. And when we're asking about whether two variables are associated, we're asking about whether these two variables co-occur. So when one of the variables is present, is the other variable present too? Are they correlated? Do they co-occur? Do they happen together? So an example would be, is skipping breakfast associated with obesity? So here we're asking if the variable of skipping breakfast is found more often among people who are obese. We're asking if these two variables are co-occurring. Another example would be, do people who eat breakfast have higher salaries? We're simply asking if the variable of eating breakfast is associated, if it's found together with people who have high salaries. The last type of question is a causal question. So here we're asking about whether one variable is responsible for changes in another variable. Or in other words, does one variable have a causal effect on another variable? Here we're going beyond describing whether these two variables occur at the same time. We're going the additional step of saying one of these variables is actually causing changes in the other variable. So an example would be, does eating breakfast enhance cognitive ability? So is eating breakfast causing changes in people's cognitive ability? It's not simply asking if these two variables are found together. It's asking something more, which is, does one of these variables cause changes in the other variable? Another example would be, does a high-protein breakfast make people feel more energized? Right? Is a high-protein breakfast responsible for changes in people's energy levels? All right. So now that we've gone over these three types of research questions, we can talk about the different types of statistics that are used to answer these different types of research questions. There's two types of statistics. One broad category is descriptive statistics. These are statistics that are used to summarize data. So this is mathematical techniques that we use to summarize or to simplify data, where we start with a large number of raw data points, hundreds, thousands of data points, and we boil all of those data points down to one or just a couple of numbers that represents that entire data set. So an average is a good example. I could have 100 raw scores, and I can boil those raw scores down into one average. Maybe the average of the raw scores is 16. That one score, 16, represents that entire data set as a whole. And so in that sense, it's simplifying the data set by making it more condensed. Now, descriptive statistics are used for all three types of research questions, but for frequency questions, all that is required are descriptive statistics. That's all you need to answer a frequency question. So here's an example frequency question. What is the typical starting salary for different undergraduate majors? Here we're asking about the frequency of earning different amounts of money given different disciplines, biology, engineering, psychology. And to answer this question, we use a descriptive statistic, which is, a mean, or the average. And you can see here that psychology majors make an average of about $32,000 after graduating college. Okay, the second type of statistic is called inferential statistics. And these are mathematical procedures or techniques that we use to generalize data from participants in our study to a larger group of people. Basically, we want to know, is what we found to be true of people in our study also true of people as a whole? Is it also true of the people who weren't selected to be a part of our study? And so this brings us to our third question, which is, how can we use small groups to answer questions about large groups? Right? Let's say we only have 20 participants in our study. That's a relatively small group, but we want to use that small group of people to answer questions about a larger group of people, maybe about people generally, people as a whole. Now, inferential statistics have to be conducted for association questions and causal questions. So only frequency questions get out of inferential statistics. So if you're conducting correlational or experimental research, that means you're asking an association or a causal question, respectively, then you have to conduct both descriptive and inferential statistics. Now, I've been throwing some jargon out at you, and hopefully it sounds familiar from Psych 301, but I've been using the terms sample and population like you know what they mean. So let's do a little review to make sure that we are on the same page. All right, so a population is the entire group of people you are interested in better understanding. It's the group of interest for your study. So let's say I'm interested in knowing whether mothers who are blindfolded, if they can detect the smell of their babies at better than chance levels. In that example, I'm interested in mothers as a whole. I'm interested in every mother out there in the world, okay? But conducting a study on every mother in the world would be incredibly impractical. It would be really time-consuming and really expensive. It's simply infeasible. So instead, I would recruit a subgroup of that population, a smaller chunk of that population, and ask them to participate in my study. So maybe, for example, instead of studying every mother in the world, I recruit women who are students at Western Oregon University and who are mothers, and see if they can detect the smell of their babies at better than chance levels. In that case, I hope that what I find to be true of my sample of mothers at WU is also true of the population as a whole. So if I find out that mothers at WU can detect their babies at better than chance levels, then I want to generalize. I want to apply that finding to women as a whole and say, yep, mothers as a whole have this ability. It's not just WU mothers. So my sample is assumed to represent the population. It's assumed to look like the population in every meaningful way. So here's an analogy I like to give. Imagine you're going through the grocery store and you spot a new flavor of Pringles, the roast turkey flavor, and you're intrigued. You want to know if this is a good flavor. Now, in order to make a determination about whether the roast turkey flavor is any good, do you have to eat every single chip in the can? Or do you just have to take a sample of chips from the can and eat those? Obviously the latter. If you did the former, if you ate every single chip in the can, that would be called a census, but that's not something we have to do. All we have to do is just get a representative sample of chips, eat those, and if we thought that those 10 chips were tasty, then we can assume that the chips that were left in the can are also tasty. But what if, by chance, we happen to draw a chip from the can that is unrepresentative? Maybe it's the burnt, ugly chip that's at the bottom of every bag, and we eat it, and it tastes awful, and so we draw the conclusion that the roast turkey flavor sucks. In that case, it would be an erroneous conclusion because our sample doesn't represent the population of chips very well. Because every other chip that was in that can wasn't burnt and wasn't ugly, and it probably tasted pretty good, if you ask me. So this raises the question, which is, how do researchers ensure that their sample represents the population? How do they ensure that their sample looks as much like the population as possible? The answer is to use a process called random selection. This is when we draw participants randomly from the entire population. Okay, so if we're truly using random selection, that means every member of the population has an equal chance of being included in my study, in the sample. So if I wanted a true random selection of mothers, that means that mothers in Russia, mothers in Brazil, mothers in Australia, mothers in Texas, they would all be equally likely to be chosen to be part of my study. Now, when I survey women who are mothers at WU, that is not true random selection because not every member of the population is equally likely to be in my study. Those who aren't members or those who aren't students at WU have no chance of being included in my study. So here's an example to illustrate. Imagine that we want to predict the outcome of a nationwide vote to approve the legalization of gay marriage. Now, because this is a nationwide vote, our population of interest is all U.S. voters. That's who we're interested in understanding. That's whose behavior we hoped to predict. Now, if I'm going to draw a sample of 100 voters, it may not be very good to select a sample of 100 Fox News viewers because that sample is systematically different from the population as a whole. People who watch Fox News tend to be more right-wing, tend to be more conservative than the average U.S. citizen. And so what we find to be true of Fox News viewers may not also be true of U.S. viewers as a whole. So that's not a very representative sample. This might be a little better, but not by much. A sample of 100 people who live in Alabama. Again, Alabama, Bible Belt state, deep south, they tend to be really conservative in their views as well. And so what we find to be true of them may not be true of people in the U.S. in general. This is a further improvement, a sample of 100 people from 5 randomly selected states. So let's say we draw 5 states out of a hat: Tennessee, Texas, Maine, Portland, Oregon, and Florida, right? But then people who live in Nebraska have no chance of being included in our study, and so it's not truly random selection. If we really want random selection, then we need to put the social security numbers or some identifying number of every U.S. citizen into a gigantic hat and pull out 100 names of people nationwide. That would be true random selection, and that is when our sample is most likely to represent the entire population. Okay, so if our sample is representative of a population, if our sample looks like the population we're interested in knowing more about, then we can use characteristics of our sample, or in other words, we can use information about our sample to estimate information about the population. It's like our sample stands in for the population, and whatever we find to be true of our sample, we assume is also true of our population. Now, information about samples is different from information about populations, and there's different words to describe both of those sources of information. Information about a sample is referred to as statistics. So whenever we have some number that describes a sample, that number is called a statistic. But whenever we have a number that describes an entire population, that number is referred to as a parameter. So you're going to hear these 2 words from me throughout this entire course: parameters and statistics. And generally, when I say statistics, I'm referring to information about a sample, about the participants in our study. And when I say parameters, I'm referring to information about the entire population as a whole. So this ability to use information about our sample to draw conclusions about information of our population, let me re-say that. This ability to use information about our sample to draw conclusions about the population is the basis of inferential statistics, right? So let's revisit this definition now that you've got a little more background information. So inferential statistics are mathematical techniques that we use to generalize data from participants in our study to the larger group of people, to the population from which they were drawn. And again, as a reminder, for questions that are association or causal, we have to go one step further beyond descriptive statistics, beyond describing our sample, to inferential statistics, where we get a number that indicates how accurately our sample represents the population. Okay, so random selection is great. It certainly increases our likelihood of having a representative sample, but it's not perfect because of something called sampling error. So sampling error is something that naturally occurs. It doesn't mean you goofed up in your study. It happens all of the time to everyone, the best researchers. It is a discrepancy or a difference between a sample statistic and the corresponding population parameter. So in other words, it's a difference or an error between information about your sample and information about the population. So let's take a look at this example. In this population, I look over here because I've got a second screen and it's much bigger than my laptop screen, so I don't mean to break eye contact with you. So in this example, in the population, we have 1,000 college students. That's the entire population. That's everybody that we are interested in better understanding. And here is some information, some parameters about the population. The average age is 21.3 years old. Their average IQ is 112.5. 65% of these college students are women, 35% are men. That's information that is true of the entire population. That's why these are called parameters. Now, if I were to draw randomly a sample of 5 students from that population, let's say I get Eric, Jessica, Laura, Karen, and Brian, it is very unlikely that the sample statistics will perfectly align with the population parameters. So for example, the average age of Eric, Jessica, Laura, Karen, and Brian is 19.8, not 21.3, right? And the average IQ is 104.6, not 112.5. And the sex breakdown is 60-40 instead of 65-35. So even though this sample was randomly drawn from the population, odds are it's not going to have exactly the same numbers as the population parameters. And we could do it again. We could draw a second sample of participants, another group of 5 randomly selected students, this time Tom, Kristen, Sarah, Andrew, and John. And again, their statistics, the information that describes them, is unlikely to perfectly match the information that describes the population as a whole, right? So their average age, for example, is 20.4, not 21.3. So this discrepancy, this issue of sampling error, where our sample doesn't perfectly represent the population, hence error, that poses a problem for researchers. To illustrate the problem, let me give you this example. Let's say we want to know if college students learn better by studying text on printed pages or on a computer screen. So if they're looking at hard copies of paper versus looking at information presented on a computer screen. So here we have our population of college students, and here we randomly draw, let's say, 15 participants to read text from printed pages, and we randomly draw another sample of 15 college students to read text from a computer screen, and then we record how many details of the text they remember. That's what these numbers represent. The 25, 26, 28, those are the number of details they remember. And so let's say that the participants who read from the printed page, who read the hard copies, they remembered an average, hence that M means mean, which is an average. They remembered an average of 26 details, whereas the sample of 15 participants who read from the computer screen, they remembered an average of 22 details. So now here we have a 4-point difference, 26 versus 22. What we want to know is this 4-point difference the result of sampling error? Is it the result of just, there's nothing different about these two groups except just by random luck they didn't happen to have the exact same value? Or is this 4-point difference the result of our treatment? Is it a meaningful difference, in other words, or was it just chance that these two groups didn't have the exact same score? So we're going to talk a lot more about sampling error in the future, but that is enough for now. So I'm going to leave you guys there. If you want to make sure you're truly understanding this material, then I suggest that you complete the learning check on page 11 of your textbook, and I will see you in the next lecture. Bye!